Okay, in this problem we're asked to find ZL for maximum average power transfer and the value of the maximum average power transfer to ZL. We're going to utilize our problem solving strategies entitled maximum average power transfer and applying Thevenin's theorem. And for our first one there, the maximum average power transfer, it says we need to remove the load ZL from the circuit and find the Thevenin equivalent circuit. So I'm going to circle our load ZL and indicate terminals A and B. So our task is to find the Thevenin equivalent circuit. The only difference here is now we have a dependent voltage source, which means you're going to have to calculate V open circuit and I short circuit. So to calculate V open circuit, we're going to remove ZL and we're going to analyze this circuit to find the voltage VOC. So let's look at this circuit. For instance, if we apply KCL at this node, that tells us that IX prime is equal to 3 at an angle of 10 degrees. And if we again think about how we want to analyze this, for instance, if we do nodal analysis, we'll have a node here, 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 and pick this one as a reference. We really only have one unknown node voltage, V1, at the top, because this node voltage is known. We know that current, and this node voltage is known. So we just need to apply KCL. For instance, this voltage here is 6 at an angle of 10 degrees. So now let's I'm going to call that V1 prime. Let's go in and let's solve for V1 prime now by writing a nodal equation. So we have V1 prime minus 6 at an angle of 10 over 3 plus J2. That's the current leaving that direction. Then we have V1 prime minus 6 at an angle of 0 over J3. And that's equal to 3 at an angle of 10 degrees. Because if we look here, this current comes on, it's going to go right into that node. So now if we solve for V1 prime, it's 9.21 at an angle of 39 degrees. Now we can find VOC by applying KVL around this loop. So VOC is going to be the voltage across this resistor, which is 4 times the current. So we have 4 times 3 at an angle of 10 plus V1 prime, and that gives us 20.55 at an angle of 22.56 degrees. Okay, so there's our open circuit voltage. Now we need to find the short circuit current because we've got a dependent source. So now we're going to take our circuit and we're going to connect A and B together with a short, and we're going to find the short circuit current. So here's our circuit diagram. Notice we've got a short between terminals A and B. And again, let's think about nodal analysis. Again, for instance, if we pick this as a reference, we have that node voltage is known. This one we have a constraint on. Okay. Here we have really only one unknown node voltage again, and that's the voltage V1. And let's apply KCL at this node to generate our single nodal equation. Okay. So we'll look at the current this way. We'll have V1 double prime minus 2 IX double prime over 3 plus J2. The current through here, we'll have V1 double prime minus 6 at angle of 0 over J3. And then this current, if we look, the voltage V1, because this is tied as a reference. Really, the voltage V1 double prime is across that resistor. So we have V1 double prime over 4 equal to 0. Now we need to express Ix in terms of V1, and we really, in a way, we can already see it. We said that the current flowing from left to right here is V1 double prime over 4, so Ix is minus V1 double prime over 4, so Ix double prime is equal to that. So if we substitute that in and we solve, we get V1 is 2.44 at an angle of minus 46.58. Now, if we go in and say, well, to calculate I short circuit, I'm going to need to apply KCL at that node. And if we look, I short circuit, if we apply KCL, there's going to be V1 double prime over 4 plus 3 at an angle of 10. Okay, so if we look, I short circuit's leaving the node, 3 at an angle of 10 is entering, V1 double prime over 4 is entering. And if we calculate, then I short circuit turns out to be 3.375 at an angle of 1.33 degrees. So now we've got the open circuit and I short circuit. We can calculate Z Thevenin. Okay, Z Thevenin is V open circuit over I short circuit, 20.55 at an angle of 22.56, 3.375 at an angle of 1.33, and that gives us 5.67 plus J 2.2 ohms. Okay, now we need to draw the Thevenin equivalent circuit. So our Thevenin equivalent circuit there's our Z Thevenin, V open circuit. Now we hook up Z sub L. Now, by our problem solving strategy on maximum average power transfer, we want to set ZL equal to Z Thevenin conjugate. So we would want it to be 5.67 minus J 2.2 ohms. Now let's calculate a current IL. So IL now is 20.55 at an angle of 22.56 divided by 5.67 plus J 2.2 plus 5.67 minus J 2.2, which is 1.81 at an angle of 22.56 degrees. And the average power in the load is going to be associated with the resistive part of the load. So then P sub L is 1/2 times 1.81 squared times 5.67, which is 9.29 watts.